Suppose that we've got two random variables x and y. When we were dealing with discrete random variables, we were able to write the joint probability as Px is equal to some outcome little x and y is equal to some outcome little y. And what this probability distribution tells us about is it tells us about the probability of the random variable x taking on particular values and the random variable y taking on particular values. Now, with continuous random variables, we can't write down this kind of probability simply because the probability of every single outcome is 0. So instead we have what is known as a joint probability density function. And we'd write it like this. The little f tells us that we're looking at a probability density function. We've got x and y. That's telling us that we've got the joint probability density function of x and y, and it will be a function of particular observations little x and little y. Now what we've got here in this animation is an example of a joint probability density function. The key things to note is that the volume under the probability density function is equal to 1, and the height of the probability density function is telling us about the relative likelihood of pairs of observations of x and y. So in order for this to be a well-defined probability density function, it needs to be the case that all of the probability is contained under our probability density function. So in other words, the integral over the whole range of x of the integral over the whole range of y of our probability density function needs to be equal to 1. Now we can apply exactly the same sorts of rules as we did with discrete random variables if we want to find the probability density function of x. Well, what we do is we hold x constant and we add up all of the possible probabilities across all of the possible ranges of y. So that is, if we want to find the probability density function of x, this is just equal to the integral over the full range of y of our joint probability density function. Similarly, if we want to find the probability density function of y, this is just the integral over the full range of x of our probability density function integrated with relation to x. We might also be interested in calculating the conditional probability density function, and the conditional probability density function is calculated in exactly the same way as we did before. So the probability density function of x conditional on y is equal to the joint probability density function divided by the marginal probability density function of y. Now we're going to see an example where we work through some of the maths related to this. So we have a joint probability density function for the random variables x and y, which is defined as 9 times the value of x squared times by the value of y squared, and that's defined between x being between 0 and 1 and for y being between 0 and 1. And the probability density function is 0 otherwise. And this probability density function is telling you about the relative likelihood of different pairs of observations of x and y. Now, in order for this to be a well-defined probability density function, remember, it needs to be the case that the volume under the probability density function needs to be equal to 1. So we could integrate over the full range of x, the integral from the full range of y of our probability density function. So this is our joint probability density function with relation to y and with relation to x. So applying the actual example here, we're going to look at the integral between x is equal to 0 to x is equal to 1 of the integral of from y is equal to 0 to y is equal to 1 of our probability density function in the non-zero part. And remember, the yellow integral related to y, so we're going to do the y integral first and then the white integral with relation to x, so we'll do the x integral second. So this is going to be equal to, if we're integrating this expression with relation to y, we're going to get 9x squared, that just is a constant multiplier, then the y squared is raised a power, so it'll become y cubed, and we'll divide by the new power. So this will be equal to the integral between 0 and 1 of 9x squared y cubed divided by 3 evaluated between y as being equal to 1 and 0, and we'll end up integrating that with relation to x. Now if we substitute in our limits 1 and 0, what we'll get, we've got 9 over 3, that'll just become 3x squared, times by 1 cubed minus 0 cubed, well that'll just be equal to the integral between 0 and 1 of 3x squared dx. Similarly, we can integrate this expression with relation to x, which will give us 3x cubed over 3 evaluated between 1 and 0, which is equal to 3 times by 1 over 3 minus 3 times by 0 over 3, which is just equal to 1 minus 0, which is equal to 1. So therefore, since the volume under our probability density function is equal to 1, this is a well-defined probability density function. Now we want to calculate the marginal probability density function of x. Now, if this had been a discrete random variable, what we would do is we would add up the joint probabilities across all of the possible values of y, which would give us the probability that x is equal to some value little x. Now with a continuous random variable, we do exactly the same thing, except we replace the sum with an integral. So we're going to integrate our joint probability density function over the full range of y. So substituting in our probability density function, this is going to be equal to the integral between y is equal to 0 to y is equal to 1 of 9x squared y squared dy, which is going to be equal to 9x squared is just a constant multiplier with relation to y. The y squared, we raise the power and we divide by the new power, giving us that this is equal to 9x squared times by y cubed, all divided by 3. And that's going to be evaluated between y is equal to 1 and y is equal to 0. And this is going to be equal to 9x squared over 3 times by 1 minus 9x squared over 3 times by 0, which is equal to 9x squared over 3 times by 1. Well, we've got 9 over 3, that's just 3x squared. Then 9x squared over 3 times by 0, that's just going to be 0. This is going to be equal to 3x squared. Similarly, if we want to find the probability density function of y, the marginal probability density function of y, we're going to integrate our joint probability density function over the full range of x, which is going to be equal to the integral between x is equal to 0 and x is equal to 1 of 9x squared y squared dx, and this is going to be equal to 9x cubed y squared over 3 evaluated between 1 and 0. And if we substitute in those limits, what we get is 3y squared. So we've managed to calculate the marginal probability density function of x and y, but you should note that this probability density function is only non-zero for the range where the joint probability density function is also non-zero. So for x, it's between 0 and 1, and similarly for y, it's between 0 and 1. Now, based on this, we want to calculate the conditional distribution of y given x. So we can find the conditional distribution of y given x using the following notation. F of y given x, this is the probability density function of y conditional on the value of x, and this is just going to be equal to the joint probability density function divided by the marginal probability density function of x. We're conditioning on x, and just like with discrete random variables, we're dividing the joint probability density function by the marginal probability density function of x. And if we substitute in our functions, this is going to be equal to our joint probability density function is 9x squared y squared. So this is 9x squared y squared. We know that the marginal probability density function of x is 3x squared, so we divide through by 3x squared, and this gives us a conditional probability density function of the x squareds cancel. We've got 9 divided by 3, which is going to be equal to 3y squared. But what you should notice is that the conditional probability density function here is exactly the same as the marginal probability density function of y. They're both 3y squared between 0 is less than or equal to y is less than or equal to 1. So that's telling us that the two random variables are independent. So since the marginal probability density function of y is equal to the conditional probability density function of y given x, this means that x and y are independent random variables.